You know, sometimes in science, you think a question is settled, done, case closed. Well, today we're diving into a story about a physical law that's been in the books for over 170 years, and it turns out there's a huge new twist. It's one of those classic tales where science thought it had the full picture, but a massive piece of the puzzle was hiding in plain sight the entire time.
All right, so let's set the stage. We've got to go all the way back to 1845. The legendary Michael Faraday is in his lab, and he discovers something absolutely foundational. He finds that if you take a beam of light, pass it through a specific material, and apply a magnetic field, the light itself actually twists. Its polarization rotates. This blew people's minds. It became known as the Faraday effect, and it was the very first proof that light and magnetism are deeply, fundamentally connected.
This discovery literally created a whole new field of physics we now call magneto-optics. And for, get this, more than a century and a half, we all thought we knew the whole story. We thought we had it all figured out. But we didn't. Turns out, something really significant was missing. A key player was sitting on the sidelines, and we never even noticed.
So here's what we're going to do. We'll start with that 170-year-old discovery. Then we're going to flip the script and look at its inverse. We'll uncover this hidden magnetic force of light and see how it completely rewrites our understanding of the original effect. And finally, we'll get into why these two effects aren't a perfect mirror of each other and why this whole thing is such a big deal. All right, let's dive in. First up, that 170-year-old twist that got this whole ball rolling. And the timeline here is just wild. So, 1845, Faraday makes his big discovery. Then, crickets for a long time. We jump forward over 100 years to 1966, when scientists finally come up with a theory for an inverse version of the effect. But it took until just now for researchers to pinpoint the crucial, overlooked role of light's own magnetic field. Think about that. Almost 200 years for a major piece of the physics to stay hidden. Now, this idea of an inverse effect, this is where things get really interesting. Let's flip the script. The question is super intuitive, right? If a magnet can mess with light, could light mess with a magnet? Or better yet, could a powerful enough flash of light actually create magnetism in a material, even just for an instant?
And the answer is a huge yes. It's a real thing, and it's called the inverse Faraday effect, or IFE for short. So with the original effect, you've got a magnet twisting light. Simple. With the inverse, you flip it. You blast a material with a really specific kind of light. Imagine the light wave is spinning like a corkscrew as it travels. That's called circularly polarized light. And bam, that pulse of spinning light actually induces magnetism in the material. The cause and effect are totally swapped.
But here's the catch, the crucial assumption that's stuck around for decades. Everyone believed this inverse effect was basically all thanks to light's electric field. You know, light is an electromagnetic wave, right? It has both an electric and a magnetic part. The thinking was the electric part did all the heavy lifting, and the magnetic part was, well, kind of pathetic. Just a minor player, totally negligible. Well, that assumption just got completely blown out of the water. Which brings us right to the heart of this new discovery, light's hidden magnetic force. This is where it all clicks into place. A team of researchers built a brand new model from the ground up, but this time they didn't ignore the magnetic field of light. They treated it as a serious contributor. And what happened? Their model perfectly explained all these weird experimental results that had been bugging physicists for years. Things like how the effect scales with laser power, or why it depends on whether the light is spinning left or right. It all made sense now. The magnetic field, that was the missing piece of the puzzle. Okay, so big news for the inverse effect. Light's magnetic field is a way bigger deal than we thought. But wait a minute, that opens up a massive question. What does this mean for the original classic Faraday effect from 1845? We have to go back and check the original case file. So here's the million-dollar question. How much does this forgotten force actually contribute to the original effect, the one that started it all? Is it like a tiny 0.1% correction that only physicists care about? Or is it something more substantial? Oh, it is not a small correction. The answer is, well, it's a shockingly big number, actually. Get this. In a super common material they use for optics all the time, the researchers calculated that light's own magnetic field is responsible for a whopping 17.5% of the total Faraday effect. That is not a rounding error. That is a huge chunk of the entire effect that was just invisible to us, hiding in plain sight for almost 200 years. So let's break that down. The electric field is still the star player, for sure. It's doing about 82.5% of the work. But that 17.5% from the magnetic field, that's not just a bench warmer. That's a key player on the team. It's way too big to ignore. This fundamentally changes how we have to think about this basic interaction between light and matter. And this discovery leads to something even deeper, a really cool quirk in the physics here. It shows us that the original effect and its inverse, they aren't perfect mirror images of each other. In physics, there's this idea of reciprocity, where if A causes B, B should cause A in the same way. Well, that breaks down here. See, you can measure the strength of both of these effects. And you'd think they'd be equal, right? A perfect reflection. But they're not. For the original Faraday effect, its strength is basically baked into the material itself. It's a fundamental property. But for the inverse effect, the strength depends on the nitty-gritty details of the laser you're using, how long the pulse is, its shape, and so on. They're playing by two totally different rulebooks. So the big takeaway here is that they are not the same. They're not mirror images. And that's a huge clue, because it tells us they're happening in fundamentally different physical environments. One is in a calm, stable equilibrium world. The other is happening in the chaotic, super fast, blink-and-you-miss-it world of non-equilibrium physics. Okay, so let's zoom out. Why does any of this matter? I mean, it's a 170-year-old physics effect. What's the big picture here? All right, here are the key takeaways. 1, we finally have the full story on both the Faraday effect and its inverse. 2, light's magnetic field isn't a footnote. It's a main character in the story of magneto-optics. 3, this completely changes our fundamental understanding of how light and magnetism talk to each other on ridiculously fast timescales. And 4, and this is the really exciting part, it opens up all sorts of new questions for researchers and could even point the way to new technologies down the road. And that, to me, is what's so awesome about science. If a force this important could be overlooked, and in effect we thought we had nailed down for 170 years, it just makes you wonder, doesn't it? What other settled facts or fundamental assumptions are out there, just waiting for the right person to come along and ask a new question?